Welcome to the next lesson, which is number 6, which can be found in your textbook in section 8.2. This lesson is pretty long, so it is going to be divided into 2 parts. So today we're going to look at part 1. The title of today is The Equilibrium of Weak Acids and Bases. Previously, we were looking at strong acids and bases yesterday, and hopefully you already have all of those memorized. Today we're going to focus on the weak ones. So first we're going to look at pure water, which is a poor conductor of electricity, and the reason for that is that very few ions dissociate. So remember, with our strong acid, about 99% of a strong acid will actually dissociate into water, so break up into its ions, where water rarely ever will break up into its respective ions. However, at 25 degrees Celsius, we can then say that the concentration of the hydronium ions is equal to the concentration of the hydroxide ions. So those two are equal at 25 degrees Celsius. They will have a concentration of 1.0 times 10 to the negative 7. So this is an important number to keep in mind, and it will be helpful when we start to do calculations. So just kind of make a note of that number. If we do write out the equation to write out the dissociation of water, we see that water will break up into hydronium ions as well as hydroxide ions. And like any equation, we do need to balance it. So you'll see on the the right-hand side, we have 4 hydrogens. So we have 3 with the hydronium and 1 with the hydroxide. So in order to balance that out, we need to put a 2 in front so that we have 4 hydrogen and 2 oxygen. Looking back at writing out our equilibrium formulas from 7.3, so our last unit, remember that we always do products over reactants. So in this case, you'll see on top we have our concentration of our hydronium ions multiplied by the concentration of our hydroxide ions. And then we divide that by our water, and you'll see here we have power to the power of 2, and that's because of our 2 moles in front here. We can then rearrange this formula and bring the water to the power of 2 to the other side. And we can substitute that value that we got from above up here, 1.0 times 10 to the negative 7. So because it represents the concentration of both the hydronium ions as well as the hydroxide ions, we can multiply those two together by substituting those values in. And we end up with 1.0 times 10 to the negative 14. We actually call this the Kw value. So our first equation that we're going to learn today out of about 6 is that Kw is equal to the concentration of the hydronium ions. These equations will be given to you for your test, but it's good to start to memorize them so you don't have to keep referring back to them and wasting time on a test or a quiz. Kw is equal to the concentration of the hydronium ions times the concentration of the hydroxide ions. We can say that that is equal to 1.0 times 10 to the negative 14. So this is our first equation. If you look in the box there to the right, the first point states that the concentration of the hydronium ions of a strong acid is equal to the dissolved acid. We basically learned that yesterday when we were talking about strong acids, but I'll rewrite it for you. Remember that because a strong acid completely dissociates, whatever the concentration of those hydronium ions that are floating around there, it makes it equal to whatever the concentration of the acid is. So if you know one, you can find the other. Good thing to keep in mind, especially for a lab that we're going to do following this week. If you're dealing with a very dilute acid, so the solution maybe is about 1.0 times 10 to the negative 7 moles per liter. The dissociation of water molecules can actually be ignored when determining the concentration of hydronium ions of a strong acid. So, dissociation of water can be ignored. It might not make a little bit of sense right now, but we're going to actually go back into quadratics again, like we learned in 7.3. However, because you can ignore the water molecules, it does make the equation a lot easier and less likely for you to have to do a quadratic. Like I said, it might not make sense right now, but as we go through a question, and more in 8.2 part 2, then it will make a little bit more sense. But just keep that in mind. The second equation that we're going to learn is how to find the pH of something. So if in the question you're given the concentration of your hydronium ions, and it asks you to find the pH, you just need to substitute it into this equation here. So you're going to take the negative log of the concentration of your hydronium ions. Remember that for the pH, an acid runs from 1 to 7, and a base is from 7 to 14. And we know that 7 represents neutral, and that's why I have 7 in both of them. So if you ever need the pH, you need to figure out the pH of something, you're going to substitute it into that equation. So we're going to call that equation number 2. The third equation that you need to know is something called the pOH, which is different than the pH because we're focusing in on the hydroxide ions rather than the hydrogen ions. So if you are given the concentration of your hydroxide ions, then you take the negative log of that concentration, and that will give you your pOH. If you add your pH and your pOH together, they should add up to 14. Hey, remember that, like I said, the range of a pH scale runs from 0 to 14, so if you add the pH and the pOH, you get 14, and this we consider as equation number 4. The fifth and sixth equation that we're going to learn is in that box on the right-hand side. So maybe you want to do the reverse. Maybe you know the pH or the pOH, and you want to find the concentration of your hydronium ions or the concentration of your hydroxide ions. So in that case, we would use these equations over here. So we consider this equation number 5 and this equation number 6. So we're going to use the anti-log, so the inverse log, which would be 10 to the x. You should have that on your calculator. If not, make sure that you ask me in class tomorrow on how to type it into your calculator. But if you're given the pH, you're just going to substitute that value into your pH. So say it was 2.75. You're going to put 10 to the anti-log of negative 2.75. That will come out with a concentration, and that would be your concentration of hydronium ions. Make sure that you are really aware of the difference between the pH and the pOH. They are not interchangeable. So if it says pH, you're looking at the concentration of hydronium ions. If it says pOH, you're looking at the concentration of the hydroxide ions. Okay? So those are all the equations that you need to know. So I've numbered them for you so that when we start to do questions in the examples, that you can actually follow along the equations and refer back to the ones I'm looking at. Acid dissociation constant Ka. So before we were looking at KEQ or Kc, and that represented the constant equilibrium. So now we're going to look at acid dissociation, so the breakdown of an acid into its respective ions. Weak acids do not completely dissociate in water. Like I've said this about 100 times now. So remember, strong acids, about 99% of it dissociates. Weak acids, only about 1% dissociates. For monoprotic acids, mono meaning 1, the concentration of the hydronium ions depends on the concentration of the initial acid and the amount that actually dissociates. So the difference between monoprotic and something else, it depends on how many protons it can actually donate. So for example, if we have hydrochloric acid versus hydrosulfuric acid, because chlorine can only give away one hydrogen, we call that monoprotic acids. And when you look at tomorrow's lessons, we're actually going to learn about something called polyprotic acids. Which just means they have the ability to donate more than one hydrogen. Today, though, we're only going to focus on monoprotic acids. So just like we learned in 7.3, we can write out an equation and then substitute it into our K equation where we do products over reactants. So in this case, wherever it says A, it's just interchangeable for an acid. Okay, so this is only focusing on acids right now. When we get into 8.3, we're going to look at it from the base side. So looking at acids, this A represents any sort of acid. We know it's an acid because it contains a hydrogen. If we take that acid and we add water to it, the ions will break up. We'll get our hydronium ions, and then the acid would be now a conjugated base floating around without that hydrogen because it has been donated to the base. This is from yesterday's lesson. So if we take that equation, no matter what, the way you're going to write out these equations, so if it's not given to you in the question, you just take the acid, you add water to it. That water will always become a hydronium ion, and the acid will always lose a hydrogen. Just a way to help you remember how to write it out. Acid plus water, the water becomes a hydronium ion because it has accepted that proton. The acid will always donate a proton and be one less hydrogen. Okay? We can take those and we can substitute them into our equation that we already know, products over reactants. So hence why we have the concentration of our hydronium ion and the concentration of the acid minus the hydrogen on top divided by that acid and water. But remember what I said way up here, the dissociation of water can actually be ignored. So really, the actual equation would look like this without the water. So really every single time when you do the dissociation of an acid, you can cancel out water and not make it part of your Ka. So before, remember, we're using Kc and Keq. Today, when we're looking at the acid dissociation, we use Ka instead. So the dissociation would be this. Okay, if you were actually given values, you could substitute those values in, and then you could solve for your Ka, which is what we're going to do in part 2 tomorrow. Okay, so let's do some examples together now, and we'll work how to use those equations, the 6 equations that we've learned from above. Okay, so the questions we're going to look at are found on page 390, and we're going to do example problem number 12. So the question says that hydronium ion concentration is 1.7 times 10 to the negative 14 in a solution of calcium hydroxide. What is the molar concentration of the calcium hydroxide? Just remember that when you see the word molar, right, it just doesn't say what is the concentration. What is the molar concentration? So what is that concentration for 1 mole? Okay, keep that in mind while we go through this question. So let's just write what we have given. So we know, it seems redundant that I'm writing it right on below it, but the concentration of the hydronium ions is equal to 1.7 times 10 to the negative 14. So it asked us for the molar concentration of calcium hydroxide. So calcium hydroxide, we can write out an equation of how calcium hydroxide actually dissociates. We know that calcium hydroxide is a strong base, and it's going to break up into its respective ions because it's a strong base. So we're going to have OH to the -1, and we're going to end up with calcium, which has a charge of +2. So like any equation, we need to actually balance that. So because we have two hydroxides on the left-hand side, we need to substitute, or not substitute, but put a 2 in here. So this would be our equation. So because we're dealing with hydroxide ions, it's not going to help us to have these hydronium ions that are given in the question. We want to know what the concentration of our hydroxide ion is, so that then we can in turn find the concentration of our calcium hydroxide by doing a mole ratio. So we need to find this. So we need to choose one of the 6 equations above and figure out how we can actually find our hydroxide ions. And the one we're going to use is actually equation number 1. So the first one that we learned up on your note back there. So that equation is Kw is equal to the concentration of our hydronium ions times the concentration of our hydroxide ions. So Kw never changes. We know that Kw is 1.0 times 10 to the -14. Again, this is in your note. I'm not making these numbers up. We want to rearrange this equation so that we can find concentration of the hydroxide ions. So we bring the concentration of hydronium ions to the other side, and we end up with the concentration of hydroxide ions is equal to Kw divided by the concentration of our hydronium ions. So let's substitute the values in that we have. Kw never changes, it's a constant, so it's going to be 1.0 times 10 to the -14. This is in your note if you don't understand where I'm getting this number from. The hydronium ions were given in the question, so we have written it out here, is 1.7 times 10 to the -14. If you put that into your calculator, you end up with a hydroxide concentration of 0.588 moles per liter. So now that we have the concentration of hydroxide, we now need to use that in order to find the molar concentration of our calcium hydroxide. So really, we know that this is 0.588. And what we want to find is the molar concentration of calcium hydroxide. However, if you notice, there's 2-to-1 ratio. So we need to set up a mole ratio in order to find our calcium hydroxide. So for every 2 moles of hydroxide, we have 0.588 moles per liter. If we want to know what it is for 1 mole, we're going to set up our equation like that. So we can cross multiply, we end up with 2x is equal to 0.588 times 1. This is a bracket. We want to get x by itself, so we divide everything by 2. So literally it's just 0.588 divided by 2, which gives you 0.29 moles per liter. Okay, so basically you know it would be divided by 2 because we have double the amount of moles of hydroxide ions than we do for calcium hydroxide. So by setting up that mole ratio, you can rearrange the formula and figure out that it is divided by 2. So the concentration, well, the molar concentration of calcium hydroxide is 0.29 moles per liter. Okay, so the way to really attack these questions is just focus on what your goal is and how you can get there with what you're given in the question, right? So for here we had hydronium ions. We know that the equation for calcium hydroxide only deals with hydroxide, so we need to find a method to get to hydroxide ions and away from those hydronium ions. Okay, so let's try question 2 and give you a little bit more practice. So for question 2, this is on page 393 and numbers 18. So the goals, we're going to look at finding the pH, pOH, concentration of hydronium ions, and the concentration of hydroxide ions. So a chemist dissolves some aspirin in water. The chemist then measured the pH of the solution and found it to be 2.73 at 25 degrees Celsius. What are the concentrations of the hydronium ions in the hydroxide ions of the solution? Okay, so there's a couple things we want to find. So first, let's just put out what we're given. We know that we have a pH of 2.73. Our goal of this question is to find the concentration of our hydronium ions and the concentration of our hydroxide ions. So we need to find an equation that will help us solve our goals. So by first focusing on finding the concentration of our hydroxide ions, we can see, or I can tell you, that we can use equation number 5. So if you go back into your notes and you see what equation 5 is, you'll see that it is the concentration of hydronium ions is equal to 10 to the negative pH. It's all about finding the proper equation with what you're given. I know I have pH. The only equation that I can use with pH that will give me my hydronium ions is this one on equation number 5. So now I can just substitute in to get my hydronium ion concentration. Just so you know, sometimes I forget the positives and negatives. If you can just sub those in as you go along. So we're going to have 10 to the negative 2.73. If you put that into your calculator, you end up with a concentration of 1.86 times 10 to the negative 3. Well, we'll put moles per liter. So the first part of our question has been found. We found our hydronium ions. The only thing left we have to do is to find our hydroxide ions. So there are a variety of ways that you can take to get to your hydroxide ions. So I'll show you one way first, and then show you a different way you could have taken in order to get to the same answer. So the next equation we're going to use is equation number 4. And equation number 4 is pH plus pOH is equal to 14. If we know that our pH is 2.73, we can substitute that in. And now we can solve for pOH. So we bring the 2.73 to the other side, so it'd be 14 minus 2.73, and you'd end up with a pOH of 11.27. Now that doesn't give us the concentration of our hydroxide ions, but we can now use equation 6 in order to get our concentration of our hydroxide ions. So equation 6 states that the concentration of the hydroxide ions is equal to 10 to the negative POH. If we substitute the POH we got from down there, so it's going to be 10 to the negative 11.27. You put that into your calculator, you end up with a concentration of 5.37 times 10 to the negative 12. And now we have answered the question by finding both the concentration of the hydroxide ions as well as the hydronium ions. Instead of doing equation 4 and 6, so just make note that this is an alternate route you could have taken, and if you don't even want to watch this, you can just shut the video off now. But an alternate route you could have taken is as soon as you found equation number 5 and you got your hydronium ions, instead you could have used equation number 1 again, where Kw is equal to the concentration of your hydronium ions, your hydroxide ions, multiplied by your hydronium ions. Remember, we use this equation from above, so we can rearrange it for our hydroxide ions. And literally just substitute the values in. So we found our concentration of our hydronium ions to be 1.86 times 10 to the negative 3. And we know that Kw, I'm going to just cross this off, that Kw is 1.0 times 10 to the negative 14. If you put that in your calculator, 1.0 times 10 to the negative 14 divided by 1.86 times 10 to the negative 3, you will get 5.37 times 10 to the negative 12, which you can see is exactly the same as the answer above here. Okay, so you can take a variety of different ways. As long as you still get the right answer, you're still going to get the marks. Okay, so use those equations, play around with them to try and get to the answer that you're looking for. If one equation doesn't work, use a different one. Okay, they will be available to you on your test. You don't have to memorize them, but memorizing them will save you time on the test. Okay, so that's all for today's lesson. And then we'll get into quadratics and harder stuff tomorrow.